Hello everyone, welcome to part 2 of limit laws. In part 1, we looked at the sum, difference, product, and host of other rules. We also looked at polynomial and rational functions where you could apply the limits by direct substitution. Here we will continue with one-sided limit using the laws and a look at Squeeze theorem. So let's look at this first question. Part A says, find the limit of square root of x minus 3 as x approaches 3 with a minus on the top. If you recall, you read it as x approaches 3 from the left. The minus indicates from the left. Let's write that there. So it's a one-sided limit. You're only focusing on one side of it. Part B says, find the limit of square root of x minus 3 as x approaches 3 from the right. To kind of answer this question, it is important for us to see how the graph will appear for this given function. Okay, so the function here is square root of x minus 3. So let's go ahead and do a quick sketch. You know, it is a radical. Because it's a radical, we have to understand the limitations of radical functions. Radicals cannot accept negative radicands, right? If it's an even radical, I mean. So this is a square root, so it cannot accept negative radicand. It can accept a 0 or positive numbers. So you can see that when we plug in 3 here for x, 3 minus 3 is 0, square root of 0 is 0. So that is the starting point. And so you can kind of draw your function excuse me, at 3, and the function is to the right of 3. And our focus here is what happens as we approach 3 from the left and as we approach 3 from the right. So clearly, there is no function happening on the left of 3, right? The function actually begins at 3 and moves to the right. So that is what we need to understand when we explain the result for answer A. For answer A, we say f of x is defined over this interval 3 to infinity, isn't it? This implies square root of x minus 3 is undefined to the left of 3. Clearly, there is no function happening to the left of 3, so it's undefined. And the function is not defined to the left of 3. That means the limit as x approaches 3 from the left does not exist. Remember, we said DNE. For part B, well, we did establish that it is defined to the right of 3. So let me just write that information here. Is defined to the right of 3. So limit from the right is square root of 0 minus. I keep saying 0. I'm already thinking of the answer, I think. All right, so you have square root of 0, which is 0. So your function is defined to the right of 3. Therefore, the one-sided limit exists here from the right as you approach 3 from the right, but the limit does not exist as you approach from the left. Next, we move to Squeeze theorem. The name is really sweet. It's Squeeze theorem. And it actually is very defining in the name itself. So we have a lot of algebraic techniques that we're able to use, like conjugate method or factoring and canceling. rationalizing. So we have different techniques to handle algebraic functions when we end up with a 0 over 0 condition, right? But there are times when we have difficulty even with basic trig functions in evaluating the limits for them. Therefore, the squeeze theorem comes in really handy. And as the name says, it says, well, if you have a difficult function, meaning a function that is difficult to evaluate, look for two other functions between which this function can be squeezed. So this can be illustrated in this graph here. Look at f of x, the orange, and the h of x, the navy blue. You have these two functions that are, one is happening above, one is happening below. But then your g of x is the function, the turquoise is the function that you find difficult to evaluate. So let me write that here, difficult to evaluate. So if you can find f of x and h of x, between which g of x will be squeezed, and make sure that your turquoise, the g of x, does not go below the orange or above the navy blue anywhere. So it has to be completely squeezed in there, okay? And over a certain interval, doesn't have to be for the entire function, but the interval of concern. So in this case, what we are trying to do is we were trying to find it squeezed at a particular point. This is the point of interest. So if you're finding it difficult to evaluate at A, then that is the point of interest where you're looking for a f and h so that it is all squeezed at A. Notice that all of these functions meet at that point, right? And you can see that this relates to some point L on the y-axis. So that could be your limit. So what we're saying is, if you can find f of x, that is, because it's lower than h of x, it's lesser, right? So f of x is less than or equal to g of x. It's less than or equal to h of x, right? And since f of x, if you took the limit, of f of x as x approaches A, this gives us the limit L. And as you apply the limit on h of x as x approaches A, that also points you to limit L. That means this g of x that you found difficult to evaluate is also going to go to L because it is pinched or squeezed between these two functions that both point to that limit L. And that is what is explained to us in this theorem. You see that? So if limit f of x as x approaches A is L, as well as limit h of x as x approaches A is L, then limit g of x as x approaches A also will be L. So let's kind of understand this for, I'll show you the proof for one of the examples, or one of the rules, I mean. So we have a couple of rules, okay? So we're saying limit sine x over x as x approaches 0. This is a rule, okay? If you were to plug in for 0, you get sine 0 over 0, isn't it? And that's going to give you a 0 over 0 condition. Now, this is we can't really use algebraic techniques as much here because it's a very simple function. So you can't do the conjugate. There's no idea of rationalizing here, or there's no factorizing that you could do. Because of the simple nature here, it's difficult to apply any algebraic approach. Therefore, we use the squeeze theorem, and I'm going to show you the proof. But upon using squeeze theorem, your answer for this would come out to be 1, actually. Let me see what's happening here. The answer is 1. Likewise, you have another situation where 1 minus cosine, hold on. Cosine x over x as x approaches 0 is 1. Or I think I got it the other way around. Hold on. I have a graph here. Oh yes, cosine x minus 1. Apologize. It's cosine x minus 1. Well, the answer is 1. Okay. Because I showed you the graph, let me kind of illustrate that to you here quickly before I come back for the derivation of that answer. This is sine x over x, or in this case, sine h over h, right? The first graph. As you can see, in the graph, it makes it very, very clear that as you approach x, as x approaches 0 from the left, right? As x approaches 0 from the left, you see that your graph approaches 1. As you approach 0 from the right, you notice that your graph approaches 1 again. So both sides of the of 0 approach the same limit 1. So the answer is 1. So you can see it graphically that it's 1, and that's what the answer pointed to in that rule. Likewise, cosine x minus 1 over x, or cosine h minus 1 over h. Here too, if you approach 0 from the left, your graph actually approaches 0. And if you approach 0 from the right, your graph comes from below and approaches 0. So in both these cases, both sides of the limit points to the same value 0. So the limit exists at 0. And that is what is happening here with that answer. Okay. So I'm going to show you the proof for sine x over x here. So this comes from, because it's trig, we try to construct a triangle here inside the circle. Okay. Let's assume this is a unit circle, right? So if I were to construct a triangle, right, with an angle theta, you know that this one, okay, this angle here, or rather the radian, is theta. We know that because we have the arc length formula, S equals r theta. S is the arc length, r is the radius, right? When radius is 1, right, because this is a unit circle, then radius is 1, S is the same as theta. So this theta, angle theta in radians, right? Let me make that clear. This angle theta is the same as the arc length theta, okay? So, so then we have sine theta is opposite over hypotenuse, right? We don't know what the opposite side is, but the opposite over hypotenuse, hypotenuse is radius is 1, right? Because it's a unit circle, so that is the radius. So that is 1. So this implies that the opposite side for the blue triangle is itself sine theta. So I can call this as sine theta. Agreed? Okay. So it is sine theta that we have difficulty. And so I found a way of giving you sine theta. And then I can say, well, theta is an angle between 0 and pi over 2, right? Because it's there. Now, I'm interested in constructing, see, the whole idea is trying to draw a squeeze theorem. So I'm trying to squeeze the sine theta between two things. Okay. So I'm going to take a larger triangle like that. Okay, it's going outside the circle, but that's okay because I'm maintaining the same angle theta. Okay, and this point would be 1, 0, right? And you can see that in the red triangle, this bottom, this part here, that is 1, isn't it? The base of the triangle for red is 1 because that is your radius. That's where you end. So let me define tan theta. Tan theta is opposite over adjacent. This is the red triangle, right? So we don't know what the opposite is, but the adjacent is 1 because that is your radius, isn't it? It hits the end of the circle. This implies your opposite side for the red triangle itself is tan theta. So that will be tan theta. So what we could say now is, your arc length theta, this arc length, right? This blue one, maybe I'll call it green for convenience. So this arc length theta is in between sine theta and tan theta, right? So I'll just say for theta that's between 0 and pi over 2, the arc length theta is in between sine and tan theta. Yes? This is crucial because we have trouble with finding the limit of sine x over x. So sine theta over theta is our problem. So I'm trying to involve a relation between sine theta and theta here, and then use algebra to kind of get through this. Okay, so then I have sine theta less than tan theta. I would like to divide throughout by sine theta. Let's divide this inequality throughout by sine theta. Okay. So this becomes 1 less than theta over sine theta less than, now tan is sine over cosine, isn't it? So that sine on the top for the tan and the sine in the bottom will cancel each other, leaving us with 1 over cosine theta. Does that make sense? Tan theta over sine theta, rewrite the tan theta as sine theta over cosine theta. This is what you get. But remember, our focus is this middle portion, but we want it the other way around. We want it as sine theta over theta. That means you have to, you can take the reciprocal, and when you take the reciprocal, obviously your inequality will reverse. So you're taking the reciprocal across, right? So you can kind of rearrange this if you want. Let me insert some more space here. So now we have, just try to flip it around so that you have the less than, style inequality. So I'm going to put this as cosine theta less than sine theta over theta less than 1. Okay. Now the whole idea is to allow limit or find limit when you allow x to approach 0. So limit. In this case, we don't have an x, we have a theta. So allow theta to approach 0. So apply limit throughout. Okay. All right. So we apply limit. And we had problem because we allowed theta to approach 0. If it was a different number, we would have had a different result. But when we had to approach 0, we got sine 0 over 0, that 0 over 0 condition, right? And that's the reason why we go for the squeeze theorem. And here we have squeezed this between two other functions. And you can clearly see that if you evaluated cosine theta at 0, you get cosine 0. And this is a constant function, so that's going to be 1. So you go a little further, and you can see that cosine 0 is going to be 1, and this is already 1. So the left inequality and the right inequality, both of them point to 1, thus leading to this middle inequality, middle part, to be also equal to 1. Thus, we were able to prove using squeeze theorem, or rather defining squeeze theorem through this, and we were able to find limit sine theta over theta as theta approaches 0 to be equal to 1. Okay. So we'll look at a problem similar to this one. Feel free to, replay the video portion. If you needed more time to kind of grasp it, you can always pause the video or replay it and, get the understanding, get the concept right. Okay. Evaluate an important trig limit. That's what it says. Okay. We just saw that cosine theta minus 1 over theta was 1, but this is the other way around, 1 minus cosine theta. So what do we do? Again, limit 1 minus cosine theta over theta as theta approaches 0. If I were to plug this in, I'll get 1 minus cosine 0 over 0, which is 0 over 0, 1 minus 1, 0 over 0. So we have to use a different way to handle this. Okay, now we can use algebra here because it's not, you can still think of conjugate here, right? You have 1 minus cosine theta, so its conjugate is 1 plus cosine theta. So let's try and see, before we could apply Squeeze theorem, let's see if we can approach this algebraically, and then if we need to, we could take help from Squeeze theorem, okay? Okay, so we have, I'm going to quickly go back here. I just realized that when I explained this part, I should have written a 0. I don't know why I wrote a 1, because I even showed you, let me put that equals properly. I even showed you here in the graph, right, that we approach 0. I'm sorry, I apologize for that error there, but we have that taken care of now. So cosine x minus 1 over x equals 0. So what we could do is we can approach this in one of two ways to answer this problem, right? We already have the rule, limit cosine theta minus 1 over theta, theta approaches 0 is 0. We got this already, right? Now what we could do is we could use this idea, because the whole point is that it's just moved around, right? Instead of cosine theta minus 1, we have 1 minus cosine theta. So what we could do is limit, pull a negative sign, cosine theta, erase that, cosine theta minus 1 over theta, theta approaches 0. We could do that because this 1, I can put a 1 in front of the minus. So you can see that, you're pulling out a constant. Therefore, we could pull out that negative 1 outside and do the limit. Cosine theta minus 1 over theta as theta approaches 0. And from Squeeze theorem, this whole thing is equal to 0, right? We just saw that. So then you basically have negative 1 times 0, which is 0. So you can actually conclude your answer this way, okay? But if you wanted to use algebra, you could do that too. It's going to be a roundabout method, but it's totally possible because of the ability to use conjugate here. So if you were using that or thinking of that approach, let's see how that goes. This is quite, the first method that I showed you is, let me put or, is obviously the easiest way to do it. But let's see what happens if you did use the conjugate approach. So 1 minus cosine theta over theta. If you take the conjugate, you're multiplying up and down by the conjugate of 1 minus cosine theta, which is 1 plus cosine theta. And then you will multiply across yeah, and then go ahead and distribute on the top. I'd like to do this by the side. So 1 minus cosine theta, do the FOIL method. Right. remember the cosine, the conjugate method helps you to get rid of these terms. So you get 1, apologize, this is a minus, 1 minus cosine squared theta. 1 minus cosine squared theta is sine squared theta, isn't it? We know that because that's coming from the trig identity, the Pythagorean identity. So you need to kind of recall that. So limit. This approach kind of helps you to do all your simplification by the side and just bring back the answer in here. You could distribute the denominator, but I'd like to keep it the way it is to see if I can separate them when the right time comes, which is in the next step. Okay, so the sine squared theta, what I'm planning to do is, I'm going to put it as sine theta over theta. I'm going to split up the sine squared as sine and sine. And then I have sine theta over 1 plus cosine theta. Why am I doing this? I'm doing this because we already have a rule for this one, isn't it? You know that this one has a limit as theta approaches 0. So I'm trying to capitalize on that information here. And then if you look at the second part here, this part, if you plug in 0, it is not a difficult condition, as in you don't get a 0 over 0 situation and things like that, right? Because you get a 0 over actually 1 plus 1, 2. So anyway, I'm going to call upon the product law, which allows me to separate these two functions by giving them their individual limits. So, you know, this whole thing, limit as of sine theta over theta as theta approaches 0 is equal to 1. So that is going to be my 1 times, here if I evaluate, I get sine 0 over 1 plus cosine 0. One times 0 over 1 plus 1 is 2. Cosine 0 is 1. So when you multiply these two, you get back a 0. So you got the same answer. It's just that you had to, go a little roundabout. But I wanted to show this to you to understand that there are times when you cannot directly use Squeeze theorem results for the sine theta over theta or 1 cosine theta minus 1 over theta. Those two special rules that we saw. You can't use those rules directly sometimes. And we may have to resort to some algebraic or trigonometric simplifications. When I say trigonometric, I mean using identities. So you have to go back and look at the identity sheet, which has, a host of formulas. You can at least think of 20 formulas, right? You have the Pythagorean theorem, or identity, I should say. Pythagorean identity for trigonometric functions, sum of trig functions, product, product to sum to product, half angle, double angle, reduction formula, power reduction, and so on. So you have plenty of them. So you want to keep them handy when you deal with trig functions. Okay? So we did arrive at the same answer in both these methods, obviously, but then this method kind of showed you some extra techniques that might come in handy in a different time for a different problem. All right, I hope you enjoyed this video, and I will meet you in the next one. Thank you.